Today's session part 2, network theorems. Okay, so this is where we're going to start coming up with some techniques to be able to analyze more complex circuits, okay, to determine unknown values. This is what it's all about. Analyze this circuit to find values that we don't know what they should be in theory. Okay, this is all on the slide handout I've given you, so where there's diagrams, they'll be there for you. You don't necessarily have to draw them. There are a number of these. They include the superposition theorem, which is the one we're going to look at today, Thevenin's theorem, Norton's theorem, particularly useful where we're interested in what a network does when we vary one particular resistor in it, or one load, when we're interested in the network, how it works with a varying load. And then lastly, the theorem of maximum power transfer. How can we find out what load will give us maximum power in the load? What we're going to do is concentrate initially on how we can use these theorems in DC networks, and then after we got the hang of that, we're going to apply them, see how we apply them in AC networks. Okay, so I've got a wordy description of what the superposition theorem is, and then we'll go through an example, right? And I believe through my slides, this example is used in superposition, Norton's and Thevenin's to show how the three different techniques essentially give you the same answers, but they're different ways of analysing a circuit. Superposition theorem, one way you're going to, the reason for using it is there are more than one, and we're going to work with two, not more than two, but it will work with more than two, sources of voltage or current in the circuit. So the circuit's not just got one source, it's got two or more. Yeah? In any network containing more than one source, the current in, or potential difference, across any branch in the network can be found by considering each source separately and then adding their effects. Okay, so what we do is we look at the circuit for one source, what would happen with that one source on its own. We look at the circuit with the other source and find all the currents. And then we add the currents in each individual branch together to get the overall current. That's basically what we're saying there. Okay. When we look at the contribution of one source, E1 say, we replace all the other sources in that circuit with our ideal internal resistances. Remember I said that the internal resistance of either the current or voltage source was important. When we consider E1, we take out E2 and we replace it with its ideal internal resistance, which is a short circuit for a voltage source. We then calculate all the currents, voltages, etc. We then do the same for the other source or sources, and when we've got all the results, we add all the individual currents, voltages together to get the overall. And that sounds complicated, okay? But if you're careful, and you do have to be very careful about being consistent with your current arrow and voltage arrow directions and the way you apply particularly Kirchhoff's voltage and current laws to make sure you get the right results in the end. Okay? So we're going to go through at least one example, right? And then there's more in the notes that I'm going to give you. So perhaps there'll be an opportunity to have a go at one or two in this lesson, and then come back and then work on that during the week, come back and we'll start next week's lesson with a little bit of a review. How did you get on? Okay. Anyone watching the video and working away from here is going to need to have a go at this as well. Alright? So, best illustrated through an example. So we're going to look at the example using this circuit here, and you've got that circuit in the handouts that I've given you. It is a circuit with 3 resistors. Okay, there's 2 sources in that, V1 and V2. Okay, and their directions are according to the arrows on there. We've got a current I1 flowing here, I2 from this source. Now, when you label up the complete circuit with its 2 sources in it, initially, all we can do is follow convention with our current arrows. So, focusing on this source here, there's the positive terminal, that the current should be flowing in that direction. We put a current I1 in that direction, by convention. We consider this source, current would flow that way, I2. Okay? By convention, we apply Kirchhoff's current law there. We've got 2 currents going in. We make an initial assumption that I3 must be flowing in that direction. And it's important to say we've made an assumption over these current directions at this stage. We've gone by convention and what we think should happen. That current's going to flow out of this battery in that direction, and it's going to flow out of this battery in that direction, and then all of it's going to join together and go down the middle. And I say we've made a stab at it, because what will happen is, don't worry if you eventually calculate that I2 or I1 or I3 is negative. All that means is you got the arrow on the wrong way in the first place. So if I2 comes out as negative, you've properly applied Kirchhoff's laws throughout all your calculations. It means that you had the arrow on the wrong way when you started. You made the assumption it was going that way, and under these particular circuit conditions, it's actually travelling into that battery, and effectively it's being charged. Okay? Yeah? But you have to be consistent. As you go through the process, we've got to be consistent and keep these arrows the way they are. Yeah? So the first thing to do then is take out one of the sources. I've taken out source V1. Right? I've replaced V1 with the internal resistance of an ideal voltage source, a short circuit. Yeah? That's what you have to do through this process. So V2, replaced with 0 ohms. Short circuit. Okay? Now, what we're going to do is we're going to add the current arrows as per, not normal convention, I've changed my thinking there slightly, as the original diagram, and I've changed my notes to suit it. Okay, so the original diagram had I1 going there, I3 going down there, and it had I2 currently against what we would normally expect for just a resistor in that direction. but we're going to keep them the same as we put on the original diagram. Yeah? We can also say here, by Kirchhoff's current law, I3 is equal to all the ones travelling out are equal to all the ones going in. So it must be I1 plus I2. That may well become useful. Okay, so given the information that you've currently got about that circuit, what further information can you calculate? What other information could we put on it according to conventions? Volt drops, yeah. I'll tell you what I'm going to do. Yeah. We'll put volt drops on in green. Current's going that way. Volt drop is opposite it. Yep. Current's going down. VR3 is going up. Current's going up. VR2 is going down. We might need them. But according to, given the information that we know, we got the values of 3 resistors and we got the value of a source. What can we calculate in that circuit first? Just going to have a quick look at my next slide, see what's on it. That's fine. What can we calculate there? No, because power can be done from we need to calculate one other thing first, Daniel. We could get the total power, probably, but we would still need to get something else first. There's only one thing directly we can get now from that circuit at the moment. What do we know? We know voltage. No, we don't know I1. We don't know I2 or I3, but we're interested in them. And in fact, we're going to call this one circuit A, and we're going to call that I1A, I2A, I3A. Right? Because when we look at the other half, when we look at source V2, we're going to have another 3 sets of values that we'll then bring together at the end. Okay? So what can we calculate there, boys? Total resistance. Yeah. We can do it in one go. What have we got here? We've got 2 resistors in parallel, in series with a third. Yeah? And if you find that difficult to get, just draw. You can always draw it a slightly different way, but effectively we've got that in series with a third one. What is the resistance to this total current flowing here, the current flowing from the source? It's got 2 ways to go there, followed by a single way to get back to there. Yeah? So in one go, we can calculate RT. If we do product over sum for the parallel bit, R2, R3 divided by R2 plus R3, and then add on the R1. We can do all that in one go. Right, and for that type of circuit, one resistor in series with two others in parallel, perhaps you should get used to doing all that in one go, because there's going to be some mathematical techniques later on. We're going to have an expression for the whole circuit resistance or impedance in one go. Yeah? So these values are 30 times 5 over 35 plus 6. What do we get, boys? 92.7. Let's say 92.7 ohms. Yeah. What can we, now we know the total resistance, which one of the three currents can we find? Yeah, I1A specifically. Yeah. So now we can go I1A. Do you not get that, Daniel? Yeah, actually, I don't get that either.
10.28.
I'll tell you why, right? The parallel resistance of these two must be less than 5. Because it's got to be less than the smallest one. So that's less than 5. Less than 5 plus 6, no way, makes 92.7. So something's gone wrong with the calculator there. The correct answer for that is 10.3. That's what I get for blindly following the first person, Joe. Don't be. Yeah. All right. So therefore, I1A is, we've got the total resistance. That's what this current is seeing. The total resistance has got to go through that pair and that one. So this I1A can be found using the total resistance. It is V1 over RT. What was that voltage? 12 volts? So I1A is 1.16 amps. Now what can we calculate, gents? Now that we know I1A. No, I've not asked for any powers, have I? How are you going to do that? Which volt drops can you find?
VR1.
Yeah, you could find VR1. How would that help you? I'm not saying it wouldn't, I'm asking you how would it help you? Because it will help you, but how would it help you? What did I ask for?
Yeah.
Calculate the currents in the circuit above and hence find the power dissipated in the 30 ohm resistor. So ultimately what we're interested in is the power dissipated in here. To do that we need to find I3A. We probably need to find I2A as well. Currents we're interested in. We'll find all the currents, it said. So we're finding one portion of the current here, remember? Finding just the portion due to that battery. We then got to go through this process again for the other battery, and then we'll end up with an I1A and an I1B that we add together to get the total I1 in the original circuit. Talking about it sounds very complex. Practice, if you do a bit of practice, actually do, and it's not that difficult. For the Ohm's law, total resistance, and Kirchhoff's law. So you're rightly saying, yes, you can find VR1. How do we find VR1? Current times resistance. I1A times R1, 1.16 amps times, what's the resistance of R1? 6.96, is that? Yeah, we really should round that to 7. .0 volts. We'll keep the 0.0 and then we've still got the same resolution there. Okay. So now we know that voltage. What else can we find? So this is 7 volts. 12 volts there. Yeah, we can find that. And or we can find that one too. If we find that one, what else does it mean we can find? I3A. If we find that one, we can find I2A, right? And once we know 2 of these currents, can we not use Kirchhoff's current law to find the third one? Yeah? So if we find that voltage, we can get that one. We don't need to find that voltage as well. We'd be doing 2 calculations where we can get away with 1. Alright, so we can either, how can we find VR3? Or VR2. I don't care really. Does that give you a clue? And we talked about Kirchhoff's law, voltage law before, around any loop in the circuit, all the clockwise arrows add up to the anti-clockwise arrows. Remember that or not? From first year science. It's a long while ago, I know. So we've got one clockwise arrow. That's why it's important to get these arrows on in the right direction. Yeah, two anti-clockwise arrows. So we can say by Kirchhoff's voltage law, V1, that's the only clockwise arrow on the diagram, is equal to VR1 plus VR2. And we've just calculated VR1. We know V1, so therefore if we rearrange that we can find VR2 is equal to V1 minus VR1. That's the 12 volts minus 7 equals 3 volts. Alright with that? Now we know VR2. Hang on, ain't VR2, it's VR3. Michael. Is equal to 3 volts. Now we know this is equal to 3 volts. What can we find? We could find VR2, but the problem's not asked for all the voltages, it's asked for the currents. So we know the voltage, we know the resistance, let's find the current. Yeah? So I3A is equal to VR3 over R3. That's 3 volts, and R3 is 30 ohms. 3 over 30 is 0.1 of an amp. Alright. Now what we've got to do is carefully apply Kirchhoff's current law to that node. We know this current, 1.16 amps. We know this current, 0.1 amps. Yeah. Now we're going to find that current there, carefully applying Kirchhoff's current law. We've got two currents going in, one side of the equation, one current coming out, the other side of the equation. So, by Kirchhoff's current law, KCL, I3A, that we just calculated, is equal to I1A plus I2A. Good God. Not spotted. Making that. What? What? 0.16. That's better. Where would I get 3 from? Took a long while to spot as well. This rearranges. We want to find this one. So that rearranges to, does it not? I2A is equal to I3A minus I1A. Agree with that? That's 0.16 minus 1.16 equals, I don't think I'll get that one wrong, minus 1 amp. Does that look right to you? Minus an amp. Think about it. When we put these current arrows on in the same direction as the original diagram, we said that that one was against convention. This source is trying to push current down there. Whether the overall current is in that direction or that direction will depend on what the other battery is doing, trying to push it back that way. Yeah? But if we're consistent with the current arrows and voltage arrows, when we come to pull it all together at the end, we should get the right result. So we now know I1A, I2A and I3A. So we've done that version of the circuit. We've done circuit A. What we've got to do now is do the same thing for the other source. So we're going to put our current arrows on, again in the same direction as they are on the original diagram. So I2, this time I1 is going to be against convention, isn't it? Yeah. And these are I1B, I2B, I3B. Put some voltage arrows on. Which direction do I put on for VR2? Up or down? Down, yeah. The current's going that way. VR2 must be opposite it. What about up or down for VR3? Up. Up or down for VR1? Down. Good. So now we've labelled that up, we can use all the same methods as we did before to calculate the 3 currents, I1B, I2B and I3B. Okay, so I'm going to pause that now, here to help, but I want you to follow through, copy the first one in essence, but with different values here to find the 3 currents, I1B, I2B and I3B. Please. Let's go back to that. For the purpose of the video, the results of that is that following the same method, we get 10 ohms total resistance, an amp for I2B, so we found that one. We then use the same methods as before to find the volt drop across R2. Don't really matter which ones we find some of these. By KVL, we use that particular loop to find VR3, 5 volts. We then use that to find the current due to this source through the middle resistor, and then apply Kirchhoff's current law to find the remaining current. Okay, and there are other ways you could go. No particular way is wrong, as long as you get the final answer right. Having done that, we go back to our original circuit, of which we labelled up via that method. And the question asked, what are these three currents in the circuit, and what's the power dissipated in this one in the middle? Okay, so by superposition, I1 is equal to I1A plus I1B. What was I1A? 1.17 amps. And what was I1B? Is that not a negative value?
1.
I1B.
I1B is not 0.83. That's right.
I1B
I1B is 0.83.
Oh yeah, minus
Oh, sorry,
0.83.
sorry.
Yeah, I know that as a negative value. Minus 0.83. 1.17, must make sure you get these plus minus 0.83. So it's actually 1.17 minus 0.83. Which equals 0.34 amps. So we can put that on the diagram. I1 is 0.34 amps. The direction is correct, because it's come out positive. 3. Hope all this work. I2 is equal to I2A plus I2B. What was I2A? I believe that was a negative value. Minus 1 plus I2B. 1. Really?
Yeah, that was 10 divided by 10.
Yeah, I was indeed. Before this work out equals no amps. I3, don't remember it being like that, but we'll see. I3 is I3A plus I3B. I3A was 0.16 of an amp. Plus look, almost equal to. Yeah, that's only because of the rounding of that sixth that we got a difference there. As I'm concerned about is this going to work? Okay. Now, I know I ought to change this example actually a little bit. because I know that the example in the notes that I was going to give you, it turns out that I2 overall is negative, and therefore the arrow's on the wrong way, and the second battery is being charged. Okay? But at that instant in time, under those conditions, there's actually, that battery's doing nothing in this circuit. No current flowing out of it. That's the conditions at that moment in time. We've got to get this concept now of we're analysing this circuit at an instant in time. If we change anything about it slightly, we change that load, everything's going to change, be a different instant in time. Or if the AC circuit, the voltages are changing most of the time. If there's any reactive components in the circuit, you could have a transient condition where things are changing. And therefore, the direction of that current could change. You could think about your battery discharging as being a way of modelling that, as it discharges, effectively its internal resistance is getting higher. And therefore, you're dropping more voltage within the battery, and the terminal voltage gradually reduces. Yeah, eventually your device gets to a point where it senses the voltage is below a certain point and it turns off. It says the battery's completely discharged. It isn't actually completely discharged. It's not going to provide what you need to run that circuit. Okay? But one way to think of it is, in the terms of this model, is that the internal resistance of that battery, as it discharges, is increasing. That's the way we could model that. And it is only a model. Yeah?
Isn't that pretty much guaranteed to be a simple example?
You may well get an exam question like that, Daniel. Okay? You might get one where these two sources are effectively, in terms of that one up that way and that one up the other way. It's a completely different circuit, and you've got, as long as you're careful when you apply your arrows and put your currents on, go by initial conventions initially, and then follow it through and carefully use Kirchhoff's current and voltage laws according to the arrows that you put on in the first place. I mean, you'll get the same result if in the first instance you said, I'm not going to bother with convention, I'm going to go that current that way, that current that way, that current that way. Doesn't matter. You'll still get the same result if you correctly apply the rules according to the way you've labelled the diagram. There'll be a difference in the maths and the sign of the maths, but the end result should give you the same result. Okay? I'm going to give you some notes now that's got this bit in it, and that's got some stuff that we're going to do next week in it. For those watching the video, the job between now and next week is to have a look at the notes on superposition in the Use network theorems to solve DC circuit problems attached to this week's work, and then have a go at the 4 superposition problems on pages 12 and 13 of those notes.